NumPy for data science. This lecture will teach you the basics of NumPy that are needed for data science. First things first, let's import NumPy. You will typically see NumPy imported as NP, NP being short for NumPy. We didn't cover importing a package as something else in our Survival Python course, but it is really simple. Just import the package that you want and then use the as keyword followed by whatever you want to name the package. Then you are able to refer to the package by whatever you decided to name it. Here you can see that we are importing NumPy as NP. Running this piece of code and printing the value of NP shows us that NumPy was properly imported and assigned to the variable NP. Once NumPy is imported, we have access to the whole slew of functionality that it includes. You can learn about all the functionality that NumPy includes by checking out the documentation that I have linked to in this notebook. The main reason we use NumPy is for its arrays. NumPy arrays are similar to standard Python lists, but they have more than a few additional handy features. The main draw of NumPy arrays, however, is their speed. You can do things with arrays much faster than you can do with lists. This isn't a problem when you are working with small data sets like lists of names or similar things that we looked at in Survival Python, but when we are doing data science, we are by definition working with large data sets. Computing those large data sets can be very computationally timely, especially if you are iterating over the whole set multiple times. NumPy arrays and their functions are the solution to that problem. To create a NumPy array, there are a few options. We can use NumPy's array function to convert an object into a NumPy array. np.array takes an object, typically a list, and turns it into a NumPy array. Here you can see that I have a list of integers passed into the np.array function. Running the code here, we can see that a NumPy array is created. The array itself prints just as a list would. Printing the type, we can see that the class of this object is a numpy.nd array. This nd array is what we are talking about when we refer to a NumPy array. NumPy arrays, unlike lists, are homogeneous, which means that all items within the array must be the same data type. Here, I have changed the integer 8, the list we are passing into np.array, to be a float. This time, when I run the code, we get a NumPy array of floats. NumPy takes the most complex data type that is in the list and converts all other data types to that. Here we can see that by changing the integer 7 to a string 7, it makes all of the items within the array strings, since strings are more complex than integers or floats. NumPy arrays are also multidimensional. You can have as many dimensions to your arrays as you want. For simplicity's sake, here is a 2-dimensional array. Running the code, we can see that NumPy even formats it nicely for us. We can also create NumPy arrays using some built-in NumPy functions, like this np.zeros function. Zeros make an array that is full of zeros. Zero's first argument specifies the shape of the array we want to create. Here we are passing in a 5 to indicate that we would like an array of zeros with length 5. Running the code, we see that we get just that. As I mentioned, the first argument in zeros is the shape. So, we can pass in a tuple to represent the shape of a multidimensional array. Here I'm looking for a 5 by 5 array, which NumPy gladly creates. Similarly, we can create an array of all ones using the np.ones function. After running the code, we again see the output is as expected. Another handy function is np.linspace. Linspace creates an array that floats from one number to another using the number of steps specified. Here, I'm looking for Linspace to give me an array of numbers from 0 to 20, and the output array should be 5 numbers long. We can see that it produced just that. Linspace is particularly useful if you want to plot some function across a bunch of different data points. So if we wanted to evaluate a sine function from -1 to 1, we could generate a list of x values to pass into it using Linspace. Here we are doing just that. We are getting 11 evenly spaced x values from -1 to 1, and then we are passing those values into the sine function. We will talk later in this course about how we would plot this data on an XY plane to see if we would need to include more steps in our X array to clearly plot the sine curve. Another function similar to Linspace NumPy has is arange. Arange makes an array across a range given a particular step size. Arange is nice because it lets you specify the step size rather than the number of steps. The default step size is 1. The default starting value is 0. Here we are creating 3 arrays. The first should be an array from 0 to 14 by 1s. The second should be counting from 5 to 14 by 1s. The last should be 0 to 15 by 4s. Running the code, we see that the output is as expected. Another useful tool that NumPy gives us is Reshape. We can take an array and turn it into any shape that we want. So here I'm making an array from 0 to 19, and then I'm reshaping it to be 5 rows and 4 columns. As you can see, NumPy just makes a new row anytime the row gets longer than 4 items in length. Oftentimes, we want to change our rows to columns and columns to rows. We can do that with np.t. T stands for transpose. Here we can transpose our 5x4 array from the last example and check that the columns and rows are swapped. All right, that's the basics. Now let's do something with real data. We are going to use pandas to get a data set into a NumPy array. We will discuss pandas in detail in the next lecture. For now, just know that the pandas.readCSV function takes a CSV and reads it into Python. We are using the flights dataset that was provided in the course materials for this lecture. Once the data has been loaded into our code, we can call rawdata.head to take a quick look at the data. This is a pandas function that we will discuss more in the next lecture. You can see here that we are working with a dataset of flights. We have a column representing the flight date, the departure time, the scheduled departure time, the departure delay, and a whole bunch of other columns. To get the data into a NumPy array, we can call rawdata.toNumPy. Running the code and printing the data, we see that we have a 2-dimensional NumPy array. NumPy has printed the first 3 rows, first 3 columns, last 3 rows, and last 3 columns for us. But we want to know more details about our dataset than that. Data.shape will tell us the shape of our NumPy array. In this case, we see that we have 330,000 rows and 19 columns. Data.size will tell us the total number of items in the array, which in this case is nearly 6.4 million. We already know that this is a 2-dimensional array, but if we didn't, we could check it using data.ndim. ndim returns the number of dimensions of the array, which as expected here returns 2. We can access a particular column of data using slicing, very similar to how we would slice a normal Python list. Here, we are trying to access the departure time column. A colon in the rows position says that we want all of the rows, and then a 4 in the columns position means give us column number 4. Printing the departure times, we see that NumPy gave us the column we were looking for. Printing the type, we see that the returned column was also a NumPy array, which will be helpful when we want to know more about the departure times. Before we get to that, however, I want to point out that the slicing of a NumPy array is basically identical to the slicing of a normal Python list. The only difference is that a comma is used to separate rows and columns. And if you were to have a higher order NumPy array, you would use more commas for each dimension. Here is another example. This time we are looking to get the first 5 rows of columns 3 to 5, which represent the departure time, the scheduled departure time, and the departure delay. Running the code, we see we got exactly what we wanted, 5 rows and 3 columns. Very cool, very cool. All right, so now let's do some analysis of our dataset. Let's start by analyzing the first 500 departure delays in our dataset. Here we are using .sum to find the sum of all 500 delays, .min to find the earliest a flight has left, .max to find the maximum delay, and .av to find the average delay time for a flight. These functions can be really useful for getting a quick understanding of our dataset. In this case, we learned that our delays were in minutes, and the maximum delay is more than 800 minutes. It's times like this when it can be helpful to perform mathematical operations on all of the items within an array. Numpy makes this super easy. All you do is use the standard mathematical operations in Python after the array, and Numpy automatically performs the calculation for all items within the array. To convert the departure delays to hours, I'm dividing the dataset by 60. We can see that Numpy properly divides all of the elements by 60, and we can easily see that the maximum a flight was delayed was 14 hours. All right, now that our data is in hours, let's do a bit more analysis on it. We can find the standard deviation of an array by using the std function, and we can find the variance by using the var function. Another thing that is helpful in Numpy is testing if items fit some criteria. Here we are checking if a departure delay is greater than 1 hour. Running this section of code, we see that Numpy tests each element to see which are greater than 1 hour delay. This is neat, but it is especially useful when you want to look at the values that match the criteria. This next example is how you do that. We take the exact same line of code from the prior example, departure delay hours greater than 1, and put it in brackets after our array. This returns only the values that fit the criteria we have entered. All right, that's about all I wanted to cover for Numpy. There is a ton more functionality out there that you should definitely check out. The Numpy documentation is great. I've linked it here in the notebook, but you can always just search Numpy documentation and you will find it.